Okay, what I want to do in this video is extend what we've learned so far about identifying oxidation reactions by being able to, calculate oxidation numbers of the components now to one of the general applications of redox reactions. And this has to do with using an oxidation reduction reaction in the laboratory to either produce a battery or to utilize it for a process called electrolysis, or on the other hand, these reactions can be used to determine the mass of things that are in solution. So one of the key things about these kinds of redox reactions is that the student learn how to balance the net ionic redox solution reaction, all right? And where you're going to find this in your college level course is either going to be, well, in two locations. You're going to encounter these types of balancing problems in the types of reactions chapter, which is usually early in the course, and you're also going to find this located in the electrochemistry chapter that you normally aren't going to encounter until the spring of the year. So normally balancing these kinds of equations is taught early on in the course, which I think is a really good idea actually, because once you guys get to electrochemistry, that material is going to be hard enough without also complicating it by difficult balancing operations. So what I want to do is take you through and teach you how to balance one of these net ionic equations. Normally you're going to be given the net ionic redox equation in the form that I'm demonstrating here. So only the key players are going to be present. The spectator ions are going to be absent. The technique that we're going to use to balance this equation is called the acidic method. I'll write that over here, the acidic method. And I've already, to be efficient, I've already put in the steps here that we're going to use to balance this equation. And one of the things the student needs to realize about these kinds of equations is that they cannot really be balanced by inspection. It's a lot harder to balance an equation that way than it is to follow the steps that I have illustrated here on the right side. So the student's going to need to learn these steps, and they really need to be part of your innate memory. And what I mean by that is that you need to be able to apply these steps without too much brain work. So after we've learned this equation, we also will look at some other examples, but the student over the course of the year is going to need to practice these from time to time, to keep up to speed on things. So the model system we're going to use to start with, I picked deliberately because the reaction of permanganate and iron plus 2 is one of the most common laboratories that occurs in a general chemistry lab in this section, in the types of reactions section, and is also one of the classic laboratories in an advanced placement chemistry course. So we're going to start by balancing this equation, since almost everybody out there is going to need to know how to do it anyway. All right, now, as a first step, what we want to do is separate these components into their oxidation and reduction half reactions. So what that means is we're going to separate this equation into the part that has to do with the reduction and the part that has to do with the oxidation. Now I think it's pretty easy to look at the iron here as the example, and you can see that it's going from +2 to +3. The only way that can happen is through a loss of electrons. So I think it's pretty safe to say that the iron going from iron +2 to iron +3 is our oxidation. All right, and process of elimination means that the permanganate going to the manganese +2 should be the reduction. Now, I can quickly prove this. In past videos, we learned that we can calculate the oxidation number of an element within a compound by setting up a simple equation and knowing a few rules about the other elements that are in the compound. Now for the permanganate, we see that overall the particle has a charge of -1 on it. So when we set up our little equation, we're going to have it equal to -1, because this equation is going to need to be equal to whatever the charge is on the particle. So if the charge was 0, which is obviously not really a charge, then this would be equal to 0. If this was -2, then the equation would be equal to -2. If this was equal to +3, then the equation would be equal to +3. Since we're with permanganate and the charge is -1, then the equation is equal to -1. We let manganese be the unknown, and then we know from the oxidation rules that I showed in the previous couple of videos in this area that the oxygen's -2. Now since there's 4 of them, that means the net charge on the permanganate is -8. So we set up our equation where Mn -8 is equal to -1. So the manganese in the permanganate is got an oxidation number of +7. And we see that it's going from +7 to +2. So the only way that can happen is by taking on electrons, and therefore this is in fact the reduction. Alright, now let me rewrite this and we'll see how to balance the equation. Alright, so it's going to be MnO4- going to Mn +2. Alright, now I normally so the way this is going to work is we've split the reaction into its 2 steps, and now what we're going to do is take each individual reaction and run it through the balancing steps. Normally I will choose to work with the reduction step first, but it doesn't matter what order you go in, so pick one and then launch down the steps. For this example, I'm going to go ahead and work with the permanganate side of the reaction first. So we've already met number 1. Alright, we have split the reaction into the half reactions. The next step is to balance non-O atoms. So we look and we compare the manganese on both sides of my arrow, and they're 1-to-1. So there's nothing that we need to do there. Next we move to the oxygens. We need to balance oxygen using H2Os. Well, we see that there's 4 oxygens on the left side of this arrow. So we're going to need 4 H2Os on the right side in order to balance the oxygens. In the next step, we balance the hydrogens by using H pluses. So we see in the last step where we added the waters. Now there's 8 hydrogens on the right side of my arrow. So let me rewrite the right side of the arrow. Alright, and then here's my permanganate. And we're going to add 8 H pluses here to even up the hydrogens on both sides of the arrow. Now in the last step, what we're going to do is balance the charge by using electrons. Remember that a single electron is worth -1. So quickly, if we sum the total charge on the left side, we see that it's 8 H pluses. That's 8 pluses. So +8 -1 for the permanganate charge is +7 on the left side of my arrow. And on the right side over here, all we've got is the charge on the manganese, which is +2. So we need to bring this +7 charge down to the same charge as +2. So what we're going to do is we're going to add 5 electrons to the left side of my equation. Alright, and that reduces the charge on the left side to +2. And now my charge balance is equal. And this is where we stop now with the reduction. And we move now to balancing the iron part of this deal. All right, so we go back to the steps. We've already separated into my half reactions. Now we balance non-O atoms, and we see that the ions are 1-to-1, so there's nothing to do there. And we move to the O's, and since there's no oxygen involved in this, we're done with that. We move to the H's, and we see that there are no H's to balance. We're done with that. And now we move to balancing the electron, or we balancing charge using electrons. All right, now we see that the left side of this equation is +2, and we see the right side is +3. So in order to even the charge up, what we're going to do is add an electron to the right side of my equation. And that evens the charge, because -1 + 3 is +2, which equals this left side of the equation. Now we're ready to bring our two equations together. So I'm going to go ahead and move the iron down here. All right, now, whoops, we need to inspect, sorry about that, we need to inspect the charge and the electrons. And you see right now, if I was to sum the two equations together, that the electrons are not going to cancel out. So what we're going to need to do is we're going to need to multiply this chemical equation times 5 in order to generate the same number of electrons here on the right side as we have over here on the left side. All right, now I'm going to go ahead and rewrite both equations. I'm going to move them over and rewrite them so it's absolutely clear what's going on to the viewer. So I have 5 electron in the top equation. We have 8 H pluses, 1 MnO4 minus. On the other side we have Mn plus 2. Oh, I left out my, okay, hold on. So we have Mn plus 2. Then we have 4 H2Os. Now, in the bottom equation, the new equation is going to be 5 Fe plus 2s. And then we're going to have 5 Fe plus 3s. And then we're going to have 5 electrons. Now when we go to add these up, you see these 5 electrons here cancel with these 5 electrons here. And if you get to this stage in these kinds of problems and your electrons don't balance out, you need to stop here and go back, because one of the two steps, one of the two reactions was misbalanced. And usually it's going to happen back here, right here in this step where your charge balancing, or in this step here where we carried out the same thing, but this was simpler to do by comparison to the permanganate. And now we can add the whole thing together, which I'm going to go ahead and do. So we're going to have 8 H pluses, MnO4 minus, plus 5 Fe plus 2s, going to 5 Fe plus 3s, plus Mn plus 2, plus 4 H2O. All right? All right, so that is the correct net ionic equation for the chemical oxidation reduction reaction between permanganate and iron 2.